In our new unit of solving systems of linear equations, we're going to talk about solving things both graphically and algebraically. Now, graphically ties into our last unit where we were doing lots of graphing, and algebraically we're going to talk about two methods that allow us to actually solve things without using a graph. Both of those methods will be very beneficial for later years. So, we can go into our first section. So, first off, we'll talk about a definition. And that definition being systems of equations being two or more equations that share the same values or same variables. So meaning any kind of things that we basically have two or more equations where we have x's and y's, or as long as they have the exact same variables. Now, that's not saying that if you have something in y equals mx plus b form, and then you have another equation that has something with, I don't know, a's and b's. Those are not a system of equations. We want to make sure that we have the same kind of variables so we can solve them. Now, in order to solve a system, we need to find out where the equations are equal. In other words, we're finding where two or more lines intersect. Now, if we have a blue line and a red line, well, they're intersecting, they're crossing at one point. And that exact point is a point -2, -3. Those are the coordinates of that point. And that's what we're going to be doing a lot. So in our first example, we're going to solve these systems equations by graphing. Let's see. First things first, we're going to have two equations, x subtract y equals 4, and 2x plus 3y equals 3. So let's see, I'm going to make this one red and this one green. So to manipulate this equation, first things first, I'm going to subtract the x. I know that some people may choose to add the y and then move the 4 over. That's fine too. Both of them will absolutely totally work. Just remembering though, when we subtract that x, there's still a negative y there. And the thing that we will have to make sure we're still doing though is getting the y by itself, which means dividing everything by that -1. So y equals a positive x subtract 4. Now on the other side of this, I'm going to subtract my 2x over so that I have 3y equal to -2x plus 3, and divide by my 3 to get my y alone. If you're unsure of what we're doing there, I will get some things up, but we are trying to get everything into y equals mx plus b form, where the m is our slope and the b is our y-intercept. Let's see, continuing on, -2/3 x, add 1. All right, so when we're graphing these, we talk about y equals x subtract 4. Well, that -4 is our y-intercept. From there, we would be going up 1 over 1. Please, when you're graphing them, do it for the entire length of your graph. At the same time, a positive 1 over 1 graph also means that it's the exact same as going down 1, left 1. All right, now I can actually put my line on, and when you do, you graph your lines, make sure you are being careful. You're being as accurately as possible. Now, using the technology, it may not be the nicest for me to do this. So sometimes you do have to bear with me a little bit. At the same time, you are able to graph yours quite nicely. Now, I'm just going to make this a little bit thinner. There we go, just so you can see that my points are there. And secondarily, we can graph our second line. It has a y-intercept of +1 and a slope of -2 over 3, which means we go down 2, right 3, down 2, right 3. Again, continue that for the entire graph. Same as going down 2, right 3, we'll be going up to left 3. From there, I can do my line. I know that when I'm actually graphing things nicely with a pen and paper, I can do this quite nicely. I can do this quite accurately for the simple fact that I can be very careful with how I'm graphing it, with how I'm doing my lines. I'm just going to switch it over to a green line, make it a little bit thinner, and add my arrows. So our question is our solution is asking, because we have these two equations, we're asking where are they equal? Well, they're equal right here. And the coordinates of that point are 3, -1. Always making sure that you write it as x, comma, y. Alphabetically. Makes things a lot easier. Next, we have a few other things. So we have a few different types of solutions. So the number of solutions that a linear solution can have depends on slope and the y-intercept, just like we had talked about in our last unit. Now, if that is the case, we should write any equation in which form? Well, if it talks about slope and y-intercept, we should probably write it in slope-intercept form. For the visual, that's y equals mx plus b form. And there's 3 different ways that this can happen. So if we have 2 lines, we can have one solution, which means that the slopes are different and they intersect at one point. We could potentially have no solution, just like we talked about last unit, where the slopes are the same, but the y-intercepts are different. Now, that means that there's no intersection, the lines are parallel. The special part, which I did allude to last unit, is that there could be an infinite amount of solutions. Now, another term for that is they're coincident, or coincident, however you pronounce it. I'm fine with both, but they're basically meaning slopes are the same, the y-intercepts are the same, they intersect everywhere, the lines are, in all practicality, the exact same. So let's do a solution of this one. F of x equals 2x subtract 4. Well, we know from our first unit, f of x just means y. It's a function of x, which means that we'd have a y-intercept of -4 and a slope of 2/1, which means you go up 2, right 1, on, and on, and on. Or we go down to left 1. I'm just going to change my thickness right away. Connect these wonderful dots. Draw my arrows. There's our first line. Now our second line, well, this one's not really nice to work with. We're going to have to do something with it. First thing, let's subtract the x. Let's get the y term by itself. So you'd have a -1/2 y equal to -x plus 2. Now we need to try and get rid of this y, or it's not the y, the coefficient in front, the -1/2, which means we're going to have to divide by -1/2. Another way we could actually do it is multiply both sides by -2, or every single term by -2. Because by distributing that in, a -2 and a -1/2 actually completely reduce. The 2's would reduce, we'd be left with 1, and a negative turns positive, which means that we just have y equal to and we distribute our negative 2 onto a negative x. That would be a positive 2x. And a negative 2 onto a positive 2 is negative 4, which means that we'd have a y-intercept of negative 4 and a slope of 2 over 1. Up 2 over 1. Wow, this looks eerily familiar. It must mean that they are the exact same line. They have the exact same equation. They're the exact same line. In one of our later sections, I'll talk about other equations also being equal. They don't need to necessarily look exactly the same, but they would mean that they are actually the same. But our term for here, they're coincident, which means there's actually an infinite amount of solutions. Because it's literally hitting every single one of these points along this line. It's hitting there, 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 there. I think you get my point. All right. Last question. Determine if the point 4, negative 1 is a solution to this linear system. One thing to note, we have a coordinate, x, comma, y. Well, if we want to find out whether something is a solution or not, all we have to do is plug the x's in for x and plug the y's in for y. So if we have two equations, 3x plus y equaling 11, and x subtract 2y equals 6, the question is literally asking, does it work? Can I take 3 times the x, which is 4, add a negative 1, and equal 11? 3 times 4 is 12. Adding negative 1 means just subtracting 1. Yeah, 11 equals 11. We're all good. Or if I plug this 4, negative 1 into the other equation, plug 4 in for x, negative 1 in for y. Let's see, 4, negative 2, and negative 1 is positive 2. Since 6 equals 6, we're all good, and it would be a solution. Now you're asking, well, what would make something not a solution? It'd be like a situation of, what about if 7 equals 11? Well, might be a popular gas station, but in math, 7 for sure does not equal 11. If you have your textbook, these are some absolutely fantastic questions to work on. If not, I do have some supplemental questions that you could work on to make sure you have these skills. Alrighty, have fun.